This is Lab 11, and I chose to look into the physics of legs and jumping. My problems were using a point particle system. I wanted to find out if I could find the change in rotational kinetic energy, thermal energy, and chemical energy in a jumping person. I also looked into a cat model and asked the question, can I model my cat's legs using a simple spring mass model? Using a point particle system to find K-trans and a real system to find the other energies, I found that the sum of all the energies was negative 2,113.73, and I found that my cat's legs actually very well modeled a simple spring system. Here are my initial conditions for the jumper. The mass I found to be 71.12 kilograms. The initial position of the center of mass was 1.316 meters, and I started the analysis just after he left the ground. The actual height recorded was extremely close to the theoretical height reached. Here's my tracker model of my brother jumping. I used my cat toy to calibrate the length and started tracking right after he leaves the ground. This is what the video looks like, and I plotted the Y position with respect to time, as you can see over in the right hand of the screen. This is my model for jumping. I put in the initial conditions and found K-trans for while he was in the air using a point particle system, 1/2 mv squared. I found velocity by dividing distance into time. I then put h into my position update in the real system with the gravitational potential energy to find the sum of all other energies involved using this equation. When I run my model, you can see the parabolic motion, and the code prints the sum of all of the other energies. The view is a little bit off in the model, but the ball goes up, comes down, ends where his center of mass would be. Imagine his legs under this ball, and you can see the 1.522 is the max height reached. Here's the energy data with respect to the point particle system. I found K-trans using 1/2 mv squared, and then put a real system to find the change in all of the other energies, and found it to be negative 2,113.73. Here's my data from the model. The purple is the actual jump, and the blue is the model without air resistance. The discrepancies at the end look like they may be due to air resistance, but overall, this matches the data very well. And then for my second question, for cat legs as a spring mass model, I used the momentum principle, including spring force, to update my position, and found Ks using my measured length of my cat's legs relaxed and coiled to jump. I found K to be 429.7, and below is all of the code for my position update, just like we've been doing all semester long. I found the force of gravity, the spring force, and the stretch, and applied that to a position update. Here is the tracker model of my cat as a spring model, and I tracked the Y position at the top of his hip as he jumped, landed, and recoiled. This is a code for my spring model, including the position update showed before, and then I found the gravitational potential energy, spring potential energy, and kinetic energy, adding up to find work at the end. This model was mainly using momentum principle, and then I put in the energy principle as well. And I did find the length of the relaxed spring, which was my cat's leg, to be 0.22, and the coiled length to be 0.04 meters. This is what it looks like when I run the model. I plot the Y position with respect to time, as well as the energies that I found. The yellow line is work, and it remains at 0 because there's no displacement in the system. The other lines are the other energies respectively, and the plot at the top is the y position, the time. Here's my data for this system. The purple is the cat leg, and spring mass model is in blue. As you can see, it actually fits my data very well, showing that a simple mass spring model may correctly predict leg muscle movement.